Hey everyone! In this video, we are unlocking one of the most powerful concepts in electrical engineering, and that is basically the symmetrical components. Now, if you've ever looked at a messy, unbalanced three-phase waveform from a fault and wondered how engineers make sense of it at all, this video is for you. Now, this concept is the fundamental tool that protection relays use to decide when to trip a multi-million-dollar generator or to clear a downed power line. And in here, we're going to break it down into these simple concepts such as the positive, negative, and zero sequence components into simple, understandable pieces. And by the end, you will not only know what they are, but you will also understand why they're so critical for the safety and reliability for our entire power grid. So let's get started. Let us begin with the problem. So in a perfect world, our three-phase power system is a beautiful balanced set of sine waves. And each phase has the same magnitude and is perfectly 120 degrees apart from the others. It's symmetrical, it's predictable, and our equations for it are relatively straightforward. But this ideal world doesn't exist for long. Reality hits in the form of a tree branch falling on a line, or a transformer failing, or even a severe load imbalance in a factory. And suddenly, our beautiful balanced system becomes a messy, unbalanced nightmare. And the voltages and currents are no longer equal, and the phases are all out of whack. Now, trying to analyze this chaotic system directly with our standard three-phase equations is incredibly complex. It's like trying to understand a smoothie by looking at the finished drink, rather than seeing the individual fruits that went into it. We need a better way. And in 1918, a person called Dr. Charles Legate-Fortesque gave us that better way. Now, his doctoral thesis gave us what I like to think of as a mathematical superpower, at least in the world of power engineering. Now, Fortesque proved that any unbalanced three-phase system, no matter how messy, can be decomposed or broken down into the sum of three perfectly balanced systems. And these are what we call now as the symmetrical components. So think of it like this. You have a complex musical chord, and your ears hears the overall sound, but a musician can deconstruct it into its individual notes, which is the root, the third, and the fifth. Similarly, what Fortesque theorem has done is to let us deconstruct our messy power system into the three notes. And in this case, it is deconstructed instead of the root, the third, and the fifth. It is the positive sequence, the negative sequence, and the zero sequence. The brilliance is that we can now analyze each of these simple balanced notes on its own, using all our standard tools, and then simply combine the results at the end. So now let's meet the first and most important component, which is the positive sequence. Now this is the good guy, which is representing the ideal balanced operation of the power system. Now, just like our perfect system from earlier, it has three phasors with equal magnitude and 120 degrees of separation. And crucially, its phase rotation is the standard forward ABC sequence. This is the component that does all the useful work. It is the one that creates the smooth, rotating magnetic field in induction motors, causing them to spin. And it's what generators are designed to produce. In fact, if you have a perfectly balanced system, the positive sequence is the only component you have, as it is the fundamental building block. Now, on the opposite end of the spectrum, we have the negative sequence. Now, this component also has three phasors with equal magnitude and 120 degree separation. So, what is the difference though? Well, it rotates backwards. So now its phase sequence is ACB, which is the exact opposite of the positive sequence. Now, this is not a component that exists in a healthy system. It is created when something goes wrong. For example, like a line-to-line fault where two phases touch, or a severe load imbalance. It's what we call the symptom of a problem. But its presence isn't just a symptom, it's actually harmful. Now, why is that? Well, because of its effect on the workhorse of our system, which is the rotating machinery. So here's the core of the problem. Imagine a generator rotor. It is spinning perfectly in sync with the positive sequence magnetic field. Now, the negative sequence field appears suddenly and spinning backwards. Now, from the perspective of that spinning rotor, this reverse rotating field isn't just standing still. It's whipping past at twice the synchronous speed. And if the system is at 60 Hz, the rotor sees a 120 Hz field cutting through it. And this rapidly alternating magnetic field induces a massive double frequency current in the rotor body itself, which we also would be known as the eddy current. And as we know from I squared R losses, current causes heat. But this isn't just any heat. It's going to be intense, localized heating in the massive iron of the rotor, which is very difficult to cool. And this can quickly burn the insulation, warp the metal, and lead to a catastrophic failure. And this is why negative sequence protection is a critical non-negotiable setting on any large generator or motor relay. And finally, we have the worst of the components, which is the zero sequence component. Now this one actually breaks the pattern that we have before. So forget the 120 degrees of separation, because in the zero sequence, all three-phase quantities are identical. They have the same magnitude, and most importantly, they are all perfectly in phase. They all reach their peak at the exact same time. And this represents a situation where the current in all three phases is identical and synchronized. But this creates a physical problem. So for current to flow in a loop, it needs a return path. And since all three phases are pushing current in the same direction at the same time, well, where does it all go? In this case, it has to add up and find a common return path. And that path is either the neutral wire or the earth itself. This in-phase nature has a huge and dangerous consequence. So in a four-wire system with a neutral, the currents from phase A, B, and C all add up in the neutral wire. So if each phase has a zero sequence current of I0, the neutral current isn't just a little current. It's 3 times I0. And this is a massive and often overlooked danger. In a severely unbalanced system, you can actually overload and overheat the neutral conductor even when the phase conductors are fine, which in this case creates a serious fire risk. Now on the flip side, this principle is the bedrock of ground fault protection. So by using a device called a core balance current transformer, which what it does is that it essentially measures the sum of all three-phase currents, engineers can directly measure this 3-0 sequence current, or 3I0. Now, if it's above a set of threshold, it means that there will be a ground fault. And in this case, the relay will trip the circuit to make the system safe. So to bring it all together, here is your ultimate cheat sheet. This table summarizes everything that we have discussed. So notice the key differentiators in this case, which is the phase rotation and the fact that only the zero sequence has no phase shift and absolutely requires a return path. This is the mental checklist you can use. So if you see a system with only positive sequence, it's healthy. If you detect negative sequence, you immediately think that there are danger to motors and generators. And if you detect a zero sequence, you should think that there is a ground fault. And you should check the neutral and earth connections. And this framework is incredibly powerful for troubleshooting. So where do we actually use this? Well, the single biggest application is of course in system protection. This isn't just theory. It's actually running in relay cabinets in every power plant and substation right now. Generator protection relays have a specific element that continuously calculates I2, which is the negative sequence current. So if it gets too high, the relay knows the rotor is overheating and will trip the generator off the grid to save it from destruction. Ground fault relays use I0, which is the zero sequence current, to instantly detect when a line has fallen to the ground and isolate the faulty section, preventing electrocution hazards and equipment damage. Even for large industrial motors, negative sequence protection is a standard feature. It's the invisible shield that protects our power infrastructure. Now, how do we actually find these components? Well, we do have a formula for this, and it's in the form of matrices. Now, I'm not going to go over how are we going to solve this formula, but the formula is essentially V0, V1, V2 equals to the matrix of T multiplied by the matrix VA, VB, VC. Now, as you can see here, you have the T equals to 1, 1, 1, and then the second row is 1, A square, A, and then the third one is the 1, A square, where A equals to 1 phase 120 degrees, or in real and imaginary components is minus 0.5 plus J 0.866. Before we wrap up, if you can take away only 3 things from this video, let it be these. First, a healthy balanced system has only a positive sequence component. That's what we designed for. Second, though, the appearance of negative sequence current is a direct warning of damaging heating in rotating machines, which it's a primary protection signal. And third, zero sequence current is synonymous with ground current, and its presence means we have an imbalance that involves the ground or neutral, and it's the key signal for detecting ground fault. Internalize these 3 ideas and you will have a solid practical understanding of symmetrical components.